Welcome to Beyond Chips, the Chips GU podcast, where we explore people, projects, and partnerships shaping Europe's semiconductor future. I'm Luciano Gaudio, Head of Communication at Chips Joint Undertaking.
And I'm Vasily Peglidou from the communications team. Together, we'll be your hosts as we speak with researchers, innovators, and industry leaders behind the technologies powering Europe's digital and green transition.
In every episode, we'll go behind the scene of Chips GU founded projects. We'll hear stories of collaboration, innovation, and real-world impact, from lab to the fab and practical application.
Whether you're part of the Chips JU community or just curious about how semiconductors are quietly transforming everything around us, from farming to mobility, you're in the right place.
Our conversations are guided by a shared principle: clear, respectful, and inclusive communication, just like how we work every day here at the Chips Joint Undertaking.
So let's get started and meet the people behind Europe's chip-powered future. Welcome back to another episode of Beyond Chips. Our guest today is Iakovos Mavroidis, a representative from Rebecca, a project building a full European stack for edge AI based on RISC-V. By combining CPUs, AI accelerators, and modular architectures, Rebecca is making local, efficient, and safe AI a reality for applications from consumer electronics to infrastructure. Iakovos, can you briefly explain Rebecca and its mission?
Yes, of course. So Rebecca is about rethinking how we bring artificial intelligence and security closer to where data is actually generated, which is basically the edge devices. So today, most scenarios we have AI running in the cloud or relies on highly specialized unknown hardware. This is, of course, not good because we rely on stable connection and the hardware is not known. So in Rebecca, we're developing a new generation of European edge AI computing system that can run demanding AI tasks directly on edge devices in an efficient and safe and secure manner. This is our main mission, and in order to do so, we're building a complete hardware and software stack. This is our platform, which is capable of running advanced AI workloads at the edge. So at the heart of this platform, we have a multi-core RISC-V processor subsystem. This is very important to us as this allows us to have some freedom. RISC-V is open source, and thus we can tailor this processor subsystem to our needs. Around this subsystem now we have some specialized AI and security accelerators, such as vision, neuromorphic processing, near memory processing, intrusion detection, and others. And these accelerators will enable us to run workloads that would normally require a GPU, but now we can run them at a fraction of the energy cost. Above this hardware platform, we have a safety and a security-aware software stack. This is essential because edge devices, as we know, operate in critical environments where trust and the predictable behavior is very important.
Iakovos, I noticed you mentioned several ways in which the technologies can be enhanced, such as faster processing and a fraction of the energy cost. But why is it important to build a fully European edge AI stack?
This is important for Europe's digital sovereignty. So edge AI is becoming a critical infrastructure. As we know, it powers robots, vehicles, industrial machines, medical devices, and appliances. So if Europe depends entirely on foreign chips and instruction sets and the closed ecosystems, we risk losing control over the technologies that drive our industries. It's also an economic necessity. Major European sectors like manufacturing, mobility, aerospace, energy, and consumer appliances are moving forward towards more autonomous AI-driven systems. So for Europe, if we want to have our technologies and become a consumer, not just developing hardware that depends on foreign architectures, then this is very important. So this is a path for us to innovate and remain independent from external vendors. And Europe has a strict expectations, strict rules around privacy, safety, transparency, and energy efficiency. And this is not possible if we use foreign black boxes.
That's correct. And this is in part the reason and the goals behind the European Chips Act to support European sovereignty and autonomy in this sector. You briefly mentioned safety, privacy, and transparency. So how do RISC-V CPUs and accelerator improve performance and safety?
So this is indeed a very important thing in Rebecca, and I think this is something that we need to clarify. RISC-V is an open instruction set architecture, and this allows us to customize the processor to our needs rather than adapting to a fixed commercial design. So by using this RISC-V architecture, we can add AI accelerators, integrate the safety monitors, and create deterministic low latency links to our accelerators. These accelerators then handle the heavy AI computations, delivering much better performance per watt while keeping latency predictable. Running, of course, something in hardware is more energy efficient than running this in software. So in this way, performance safety, of course, are benefit a lot. And we have a close collaboration between RISC-V cores and specialized accelerators. Instead of running everything on the CPU, intensive tasks like convolution, feature extraction, neuromorphic processing, or security monitoring are offloaded to hardware designed specifically for the operation, which is crucial under the strict energy and thermal constraints of edge devices. The result is an edge AI platform that is powerful, efficient, and inherently trustworthy.
So can you please briefly explain the role of chiplets and modular design in your approach, the approach of Rebecca?
Certainly. So this is another important aspect in Rebecca. Chiplets give us a very flexible way to build advanced computing systems without relying on one large monolithic chip. So essentially, each chiplet is a complete compute element, including the RISC-V processing subsystem and the memory interfaces, accelerators. And this complete compute element integrates everything that we need to run and boot a full system. By using the die-to-die and chip-to-chip interfaces, we can connect several of these chiplets together. So we can easily scale the architecture depending on the needs of the application. So while we have a single Rebecca die, this die can be used in several use cases depending on your use case. This modularity also improves manufacturing yield and lowers cost, because if a single chiplet has a defect, we only discard that small part rather than an entire large monolithic chip, which is very expensive, of course. The architecture also becomes more adaptable thanks to the connection with a reconfigurable external FPGA. So this is not a chiplet anymore, but we have an external connection on a reconfigurable FPGA through the chip-to-chip interface that we support. This allows us to further extend the system with additional accelerators, custom I/O modules, or experimental hardware features without redesigning the chip itself. So together, the chiplet approach and the FPGA interface give Rebecca a level of scalability, configurability, and long-term flexibility rather than traditional monolithic chips, which cannot offer all these important features.
So what kind of real-world use cases are you demonstrating, in which industries or industrial scenarios?
So an important thing for Rebecca is the use cases. So a key strength of the project is that we validate the platform in real industrial scenarios. Of course, we start with standard benchmarks to validate the platform, but the final target to use real industrial scenarios, which are not just some experiments that run in controlled test environments. For example, in the smart appliance domains, we work with Arcelic to run real-time human detection models on devices with extremely tight energy and cost constraints. There are more cases. Another example is underwater infrastructure inspection, where autonomous robots equipped with event-based cameras detect cracks in harbors. In this condition, the AI must run entirely on board in real time and under harsh environment constraints. Exactly the kind of workload that our accelerators, Rebecca, and software stack are designed for.
It's truly versatile with all the different parts that you mentioned, all the different use cases such as robotics, drones, and energy systems, which also, of course, are driving the future. What are the most challenging technical aspects, though, in your work so far? Is there something that particularly stands out for you and the team?
There were several challenges in the project. This is a really big project involving many partners. So one of the biggest challenges in Rebecca was to integrate this diverse set of hardware and software components into a single coherent architecture. As you can manage, there are many modules and many in software and hardware. And as we are 24 partners in total, each accelerator or hardware software module comes from a different team with its own interfaces, memory requirements, and timing constraints. Getting all these pieces to work smoothly together alongside the RISC-V subsystem requires significant coordination and a lot of careful engineering. Apart from the integration effort, there are major challenges related to the prototyping. We have used the FPGAs, and the FPGA-based products are excellent for early product development. They have all that we need to prototype our system. However, there is some limitations. The main limitations come from hardware and I/O resources. It is not easy to emulate the entire system at once. As a result, we had to work with partial prototypes, distributed testing environments, or even design add-on boards. For example, we had to develop a dedicated HyperRAM memory modules as we use a HyperRAM main memory to extend the capabilities of the FPGA platforms. However, while we had many challenges, the team was pretty good and reaching the point where our emulation prototype boosts Linux and communicates reliably with multiple accelerators. And this was a major milestone for us, showcasing that the integration effort is paying off and that the project is progressing strongly.
When you have such a big project, of course, challenges are coming up. But like you said, despite those challenges, it's about reaching the point where you can communicate reliably and find a solution around those challenges. But if we just take one step back and talk a little bit more about the Edge AI solutions again, how can you ensure that Edge AI solutions are secure and trustworthy?
So security is very central in Rebecca. As we have an Edge AI platform, our systems are meant to run in the real world in factories, appliances, robots, or inspection equipment, often close to people or critical infrastructure. At the hardware level, we include a dedicated intrusion detection accelerator that can monitor traffic or host pattern behavior and detect suspicious patterns. We also use formal methods and microarchitectural simulations to analyze the RISC-V core and the accelerators for vulnerabilities, including things like memory safety issues, denial of service risk, and certain classes of side channel attacks. On top of that, we perform fault injections and stress tests to see how the system behaves under failures or adversarial conditions, and we use these results to harden the architecture. On the software side, we rely on hypervisors and operating systems that are designed with isolation and safety in mind, so that different applications or workloads can interfere with each other in unexpected ways.
So if we just take a more practical outlook, the Chips GU aims to support and help SMEs and startups in adopting certain technologies, get the necessary funding in order to be able to move forward. So how does Rebecca support SMEs and startups in adopting these technologies that you mentioned?
So in Rebecca, we have 24 partners and several of them are already SMEs. This is a central goal in Rebecca. So we're creating an IP catalog that gathers all the hardware and software developed in the project. So the external partners, the SMEs, can access this IP catalog. And as I told you before, this is open. They can review it and make their adjustment. So these IPs can be used individually or combined into a complete system. This allows SMEs to adapt exactly what fits their needs without being forced into all or nothing approach. This modularity gives them a practical and affordable way to start experimenting with Edge AI capability. We also collaborate with other European projects such as ISOL and Tristand, as well as with European initiatives such as Eclipse and RISC-V Open Hardware Foundations to promote Rebecca's results and strengthen the surrounding ecosystem. Because our platform is based on open standards like RISC-V and open source software framework, SMEs avoid vendor lock-in and expensive license barriers. They can innovate at their own pace, customize the technology to their products, and even contribute back to the community.
This is important not only to you, but also to us, because what more could we want when we see not only the fact that we are funding European projects like Rebecca, but that our own projects are collaborating with each other. So do you think having this funding from the CHIPS JU has made a difference?
Yes, I think that CPGU is very important as this funding is essential for a project like Rebecca. Developing a full edge AI platform from a custom RISC-V subsystem to specialized accelerators, chiplets, and a complete software stack requires coordination and the resources that no single organization could easily manage alone. We have 24 partners, funding coming from CPGU and national agencies. This is very important to us. The funding brings industry, research centers, and the university together, provides access to advanced semiconductor tools and technology, and turns what would otherwise be small, isolated prototypes into a coherent European-owned solution. Without the support from CPGU, we would have fragmented efforts instead of a unified platform, and Europe would miss a major opportunity to strengthen its technological independence and digital sovereignty.
Thank you for your kind words. And one last question before we close off the interview. If you can visualize a little bit the future, perhaps, what would success look like to you by the end of the project?
Success for us would be to meet all our objectives. So for us, success means delivering a fully integrated European edge AI platform in silicon, a real ASIC that brings together the multi-core RISC-V Pro subsystem, the accelerators, the memory subsystem, and the chipless interfaces, all supported by a complete software stack. So having the whole software hardware platform implemented and running on an ASIC. Beyond getting the hardware to work, we want to demonstrate it through our use cases that the platform delivers clear improvements in latency, energy efficiency, safety, and security compared to traditional solutions. So one thing is implementing our platform, and the next thing is to evaluate it and get good results. So success is also about long-term impact. We want to leave behind open components, solid documentation, and an ecosystem that allows companies, especially SMEs, to take our results and build real products. As I mentioned before, the IP catalog is very important to us. Collaborating with other partners and projects is very important. If after the end of the project, the Rebecca architecture and this IP catalog continue to be adapted, extended, and integrated into European technologies, then we will have achieved not only technical success, but also meaningful progress towards Europe's digital sovereignty.
Iakovos, thank you very much for your time and for the information you gave us here today. I wish you all the best for you and the partners for the project. And I hope you do achieve all your goals.
Thank you for inviting me, Vasiliki.